Alright, so this problem deals with a similar set of things that we've done in the past with collisions, but it brings rotation into it. And so basically everything we did with collisions and conservation laws before works, but we have to now use rotational versions of that. So we're given two pictures of a before and after collision, where we start off with a rod rotating with some speed, omega, and a ball at rest. And actually, let's move that over a little. And we end up with the rod vertical at rest and the ball moving with some velocity v, right? And there's the fixed point still the same. And we're told the length of the rod, right, is d. That's the same in both. And we're told that the rod is mass m1 and the ball is mass m2. And so we need to, in doing that, describe what's going on sort of before and after with certain assumptions. So the first thing we have to do is figure out the angular momentum of the rod about the point P before the collision, right? And we see that since the rod is a symmetric object rotating about a fixed point, we can use the definition of I times omega. And we're given the moment of inertia of the rod in the problem. Right, and omega is however fast it's rotating. So that's really it. It's just substituting those pieces in, right? So you can kind of clean it up. But that's basically part A. Just kind of making sure you recognize what's going on. Really, it leads into part B, which is where we have to figure out the speed of the ball, so the linear speed v after the collision happens. And really, once you recognize that it's a collision, then all you need to think of, well, we just found an initial angular momentum, so if we could find a final angular momentum, then we could equate the two and solve. And this one, since the ball is essentially a point mass, it doesn't make sense to use the I omega definition. We want to use, right, this R cross P1. And R, I'm going to draw in red, right, is the distance from the pivot to the point of impact, right, that's R. And P is the direction of the momentum of the ball, right? And so with that, it becomes pretty easy to see what's going to happen, right? That's a 90-degree angle. And so R is just the distance d, right? That's how far it is from the pivot point. And P is just mv, and then we have the sine of 90 degrees from the cross product, which is just 1. So this is, actually, let's make it clear, this is the ball, right? m2v. And we don't care about the, well, we don't have a term for the rotation, or the angular momentum of the rod, because the rod comes to rest. This is all we have. And all we need to do, right, is just equate these two sides. And equating this and this. So we get 1/3 m1 omega d squared equals m2 dv. We can cancel a factor of d, and we get v is m1 omega d over 3 m2. And that's part B. So to do part C, we're given in the text of the problem that the collision is also elastic. And so if the collision is also elastic, then we know that the initial energy equals the final energy. And we don't have any thermal energy stuff going on, right? Whatever mechanical energy we start off with is what we end up with. And so all we need to do is take those pictures and describe their energies rather than their momenta. And so before, we have a rod rotating. So it has rotational kinetic energy. After, we have a ball moving. That's translational kinetic energy. Right, so these 1/2 will cancel. We know what the moment of inertia is. Right, it's kind of a sloppy omega. And we just found what v was in the previous problem. So we can just substitute that right in. So the d squareds will cancel, the omega squareds will cancel. We'll get rid of 1 factor of m1, 1 factor of m2, and 1 factor of 3, right? That cancels all that, like the square, because I've canceled one of each of those factors. So we get 1 equals m1 over 3 m2, right? That's all that's left. And since we want m1 over m2, we'd have to multiply both sides by 3, and so we get our final result. And if that algebra was too much cancellation, you can distribute it all out and cancel it that way too, or you can do the square and then cancel after that. All right, so that's part C. And so for part D, we're given a very slight change, right? We've changed the position that the ball is at, and we've changed the mass that it has. And so really we're trying to sort of redo parts B and C all in one, because we're told they're closer to elastic, so we know. Actually, I'm going to move on to another page so I can draw it. So our new before picture, right, it's kind of sloppy again. Kind of looks like that, and our after picture is going to look the exact same. Right, that goes at some velocity. This is rotating. There's our fixed point up at the top, D, and now these are both mass m1. Alright. So we're going to do both things. We're going to write the angular momentum before and the angular momentum after, and the energy before and the energy after. So, right, first conservation law, angular momentum is conserved in collisions. The initial angular momentum doesn't change at all, right, because that's only based on the rod. We didn't change anything about the rod. So this is still the same, right? But now the final angular momentum, right, this is what's described as the distance x, right, that length from the pivot point to the center of the ball. So that means the rod is no longer a distance d, it's a distance x, right? And you can follow the same process to see why it's x times m1v now, because it's still perpendicular, and so you're just using r cross p, but now it's a different distance. And so the masses m1 will cancel, and we'll get d squared omega over 3 equals x times v. We can also have that energy is conserved because we're told it's still elastic. And once again, the rod's rotational energy doesn't change. Right, so we can just kind of copy that straight over. Right, that's from part C. But in this case as well, the ball's energy doesn't change either, because the ball's energy doesn't care whether it's centered or at the bottom. So this is just that. But the only difference, right, is now this is m1, so those masses will cancel. And we'll get d squared omega squared over 3. Oops, I wrote an extra, this 1/2 was canceled, because it appeared on both sides, 1/2 I omega and 1/2 mv squared. So this is just equal to v squared. Right? And so this is 2 equations and 2 unknowns, and we can solve that. You cannot use the relationship between v and omega, right? Something that's like v equals omega times r or anything like that, because that's not true in this case, right? It's not an object rolling without slipping. It's not sort of a point on a rigid body. So we can't solve, right, this equation by itself by doing a relationship between omega and v. There is no relationship between those other than this conservation of energy and momentum. So we have to solve the two together. Right, so this one will lead to v is d omega over the square root of 3, which we can promptly put right in there. And so we get d squared omega over 3 equals d omega over the square root of 3 times x. We cancel a d and an omega, and we can cancel some of the 3. And so we get x equals d over the square root of 3. And that's the final answer. And so this question really just forces you to think of concepts that we've done in a rotational sense. Not anything completely new, but sort of different ways of writing it and expressing it and tracking it.